Welcome, everybody. My name is Tommy Source. I'm Assistant Director of the Purdue Institute of Inflammation, Immunology, and Infectious Disease. And today on our Purdue Lecture Hall series, I have the pleasure of welcoming Nick Morato from Graham Cook's lab in the Department of Chemistry. Welcome, welcome, Nick. I am so glad that you decided to do this and give us a brief lecture on what you're doing. I am so excited just because I love the work that comes out of the Cook's lab. And I've spoken to Graham a little bit about the work that you've been doing, and I am so excited about it. I know you probably can't go deep into it in this lecture, but I just want the audience to know that Graham Cooks and the work that you do with him. I mean, you guys are pioneers in the field of mass spectrometry and analytical chemistry, and you're really at the forefront of that whole field. And it's so exciting to and have the honor and pleasure of welcoming you to the program and hearing your story a little bit. So thank you so much.
Thank you, Tom. I really appreciate the invitation. Let me share this.
Yeah, perfect.
Okay, cool.
And so what I'll do is that I'll turn myself off. You can have the whole screen, and I'll pop back in later once you're done your presentation. Sound good?
Sure. Feel
Awesome.
free to interrupt at any time if needed.
Okay, perfect. Thank you.
Okay. So I think what I like to share with you all today is a bit of my life and my short career. And maybe see if I can leave you some lessons of what I've learned over my almost 30 years of life. So first thing that you probably should know about me is where I'm from. So I am from Bogota, which is the city in this photograph. It's a city high up in the mountains, about 2,600 meters above the sea level. So it's fairly cold because it's high up there, but we don't have seasons. It's about the same nice weather all year long. It's a 8-10 million people city, so a lot of people, a lot of things to do, a lot of traffic. But that's kind of the world in which I was born and raised, and I'm very proud of it. In case you were wondering, Bogota is the capital of Colombia, which is a country in South America. Somewhere over here. Currently, we're probably somewhere over here. And Colombia has a huge variety of everything. Geographic variety, biodiversity, variety of languages, although the official language is Spanish, so I was born and raised speaking Spanish. All sorts of people and food and so on. And for me, Colombia represents, of course, my country, and it's probably one of the main factors that made me who I am today, being born where I was born. But I always, whenever I get the chance to talk with people and talk about where I'm from, I always like to hear what people think when they hear Colombia. Of course, we cannot do that right now. But when I used to teach classes here at Purdue, I haven't in a while, I used to ask the students of my sections the first day of class, what did they think of Colombia? What comes to mind? And in some cases, it is nothing. They haven't heard anything, so that's all right. Other cases, they're pleasant or unpleasant surprises. But in any case, I'll just want to show you some postcards from Colombia. This is all in Bogota. This is the downtown Bogota, so it keeps all the colonial architecture from when the Spanish were there. Bogota is surrounded by mountains, despite of being basically in the top of a mountain. So it has a nice landscape. This is called El Peñón. It's a huge system of lakes with this huge rock that you can actually go up with little tiny staircase somewhere around the rock. Very nice place, one of the most beautiful places I've been. This up in the north of Colombia, Cartagena, the city that most people visit, very touristic place. Caño Cristales, river with a lot of colors from algae that give them that very nice red color. Cartagena again, beach, and again, we land back in Bogota. So here is where probably our story starts. And that story starts when I was finishing high school, probably. And I was trying to decide what to do with my life. Um, because at least in Colombia, the decision of what are you going to study is something you don't usually take lightly, because when you enter college, you enter with a major defined, and this is your path, and changing majors later on, it's doable, but it's not an easy process or not something that you want to go through. And so usually it's a major decision. And I was very confused because I knew what I wanted to do, but there was no way I was going to be able to do what I wanted to do. So what I really wanted, and for many years I was super obsessed. Now I'm still obsessed, but probably less obsessed. This is what I wanted to be. I wanted to be CSI. I wanted to be a part of a crime scene investigation team. I wanted to do all sorts of forensic stuff. I was, deeply in love with this world. And if I had had the chance, I would have taken it, no doubt about it. But in Colombia, there was no way of really studying any forensic related stuff at the professional level. The only option that I had at the time was to become a cop. And then after you're a cop for about 3 years, you can take a year of training on kind of crime scene investigation. And I didn't think I was cut for it. So I ended up not taking that option. And so, because I couldn't do what I really was deeply in love with, so I had to find an alternative. And that was complicated. It took many, many months of just thinking, what could I do instead? And one night, I stumbled around this website. I don't remember really if it was the exact website, but it said the exact same thing. It was from the ACS, which is the American Chemical Society, from the Division of Analytical Chemistry. And they had this kind of set of flyers and things about what different careers could you take after studying chemistry. And one of them was this, in forensic chemistry. And so I started reading, and it was a revelation. To me, it was, this is what I needed to do. This is what I should do. I could become a chemist and then become a forensic chemist. And that is the way that I learn all the things I need to learn to become a crime scene investigator. And so that solved my problems. Literally, that was late at night, whatever day it was. The next day, I registered for my college applications for chemistry. There was no turning back. That was the decision made. And that was my first interaction really with the ACS, and in particular with the Division of Analytical Chemistry, which funnily enough, later on, I don't know how many years later, 8 or whatever years later, they ended up funding my research and kind of my stay here at Purdue through a fellowship. So that went on full cycle moment with the ACS Analytical Chemistry Division. But so I started college in 2013, I think. And I went to college to this university. It's called Universidad de los Andes. So Los Andes, or the Andes, is the biggest mountain range in America, the whole continent. And it go across Colombia all the way from north to south. And Bogota is on top of the Andes mountain range, so that's where the university gets its name for. It's a part of the campus. It's kind of it's close to downtown Bogota, but it's really, let's kind of the outskirts of the city. This is right on top of the border of the mountain. So you can enter through here, and the chemistry department is this building right here. It doesn't look like it, but it's probably the farthest apart and the highest up in the mountain from all of them. So I was always late. So I had always to basically sprint or kind of climb the mountain to get there completely out of breath. That was my day to day. But interestingly enough, the gym is this building over here. So if you want to get there, you did all the exercise you needed to do just to get there, which that was always quite funny. And so I started to study chemistry. And there was a decision that I made based on this future prospect that I had on eventually coming first to chemistry, then CSI. I had this timeline planned. And then a lot of noise started leaking into my head. In particular, remember very clearly the first lab of the chemistry program. We had a TA, the person teaching the lab. I think he was very regretful about his life in a way, but all the time was just complaining. At the time, he was finishing his master's in chemistry after doing a bachelor's in chemistry. He was just complaining about, why would anyone pick this? Why would you pick something that will give you good money? Why would you pick something that will basically force you to be a slave in the lab 24/7? Why will anyone pick this career and so on? And it's sad because you're telling that to people that are just starting their careers, their studies after they made the decision to pursue it. And so that made you hate what you're doing, that made you second guess yourself a lot. And at the time I was probably not wise or confident enough to just tell him to shut up. But so that's a lot of things that start getting in your head. And so for my second semester in college, I was doubting everything. And I just decided to start a second major. So I ended up studying also industrial engineering because that was kind of my backup. If chemistry was not going to work, at least I should be able to get a job as an industrial engineer. These people are everywhere and they do everything in every single company. So that should work. That will be the backup. And that was a decision that I made based on fear. But at the end of the day, I think being an engineer made me be a better scientist. And so I do not regret it. But I do think one should learn to trust in yourself more and stop second guessing so much based on whatever people say. So that's a bit of an advice there. But when I was finishing college, back in my school, we have to do a full undergrad dissertation. So we do a semester of research and we end up with a dissertation and a defense. And so I decided, after looking some options, to work with Professor Chiara Carazzone, who still leads this Laboratory of Advanced Analytical Techniques in Natural Products. And so it's the second time that this kind of analytical chemistry team has popped up in my story. So let me just tell you a bit on analytical chemistry. What the hell does analytical chemistry mean? Well, analytical chemistry is basically a measurement science. You want to measure things. You want to find what things are made of. You want to find the components in the sample. And you also want to be able to quantify the components of that sample. So analytical chemistry is everywhere. In pharmaceutical industry, there has to be someone that guarantees that they're putting the right amount of antibiotic on each pill, right amount of whatever medicine on each pill, that everything that is supposed to be there is there, and that everything that is not supposed to be there is not there. There are, of course, for example, in crime scene investigations, there are the people that find if there are drugs on the scene, if the dirt sample of the crime scene is the same dirt that is on the suspect's home. And so it's widely applicable, and it usually involves the development and also the work with a lot of instrumentation that looks something like this. And so that is what I decided to go into. Of course, it fitted into my timeline, my plan of life that I had. Chemist, forensic chemist, CSI. That was the road so analytical chemistry is what took me closer because that's really what I needed to learn. And so that's why I decided to start working with DET, which was applying analytical chemistry in particular to natural products, which, Colombia is a great place to do so based on all the biodiversity we have. And so I'm going to have a lot of pictures of people across these slides. That's probably the second piece of advice that I could give is really surround yourself with people that support you, with people that help you grow. And I think I would have gotten nowhere without the people that I met along the way and the mentors that I had, including, of course, Yara. Because really the people that are around you you become the people that are around you. So surround yourself with good people. So I started working with Yara, and she was very gracious. She gave me a couple of options and things that I could do. She knew I wanted to do forensics, so we tried to find something similar. So maybe something with poisons or venoms, because, some connections there. So from the options that she gave me, I like this one about working with the snake venoms. It sounded pretty cool, pretty like movie-like type of thing. So she had some venom samples from the snakes of this species, Botrops atrox, which were collected in north of Colombia, if you remember the map. And those venoms were collected by this person. So second picture showing up, Andres Tibabuso, which at the time for me was just, random crazy dude that went to the middle of nowhere in the desert to find the snakes to get venom from them. So to me, it was just this random biology dude. Later on, he's gonna come back to this story. But we had those venom samples, and we had samples from small baby snakes. So they're called juvenile snakes, typically under 4 years old, and also venom from adult snakes, older than 4 years. And then one can ask a simple question. Are there any difference in the venom of the adult snakes compared to the baby snakes? So that was a question that she gave me. And I hope that brings some questions to you. For example, why on earth are we talking about the snake venoms? Who cares about the snake venoms? So why do we care about the snake venoms? Well, one of the reasons why people should care about the snake venoms is because a lot of people still die after being bitten by snakes. So maybe not so much in the States, but closer to the tropical regions, there's a lot of people dying because of a snake bites. So if you don't know what is in a venom, it's difficult to develop and test antidotes for the venom. So knowing the composition of the venom, again, analytical chemistry, measurement science, we're trying to find what is in the venom, how much of everything that is in the venom is there, becomes important. If that's not good enough reason, well, second reason is if you want to discover new medicines, maybe you want to look at nature. Nature is pretty smart. It has been doing chemical synthesis for billions of years. So it probably does it way better than we do. And it does. So there are many, these are just a couple of examples of available commercial FDA approved medicines that have come from snake venoms, as they were on the venom or analogs or slight modifications, but in some way or form they've come from snake venoms. One of the biggest examples is captopril. It's a medicine that is used to treat hypertension, high blood pressure. And it's probably one of the most widely sold drugs in the world. And it came from a snake venom. So that is another reason why people should care about the snake venoms, at least in my opinion. So that's one of the questions that might pop up your head. Second question is then, okay, well, venoms are interesting, venoms are important, great. Why do you care if the venom of baby snake is different from the venom of adult snake? And eventually, babies are different from adults and humans too, so why do you care? And there are different answers to that question. So one of them is related to the antidotes. So if antidotes are typically made based on the venom of adult snakes, what if the venom of baby snake is too different? so different that the antidote of adult snake doesn't work for it. So if you get bitten by baby snake, well, sorry, you die because the antidote that we had didn't work for it. So you need to know what difference are between these two venoms in order to be able to develop better antidotes. Same with drug discovery. You don't know what compounds, new compounds might the baby venom, the baby snake have compared to the adult snake on their venoms. But then why do we think there's even a difference? Why couldn't it be just the same venom? Why are we wasting our time? Well, there is some things in their biology that might indicate that there is a difference. For example, baby snakes are small, so they can eat only small things like insects and small lizards. And if you think of it, these are prey that are difficult to see, difficult to catch, difficult to hold, and that could escape very easily. So baby snake might have a lot of neurotoxins on their venom to try to, as soon as it bites one of the prey, it just freezes it, just completely kills it right there so that they cannot escape, they cannot move, and so you can eat it. You don't have to chase it. But the adult snake can eat bigger things, like small mammals. So the venom maybe now is not so rich in neurotoxins because the snake is so big that can actually grab the prey and just hold it by itself with its own body. Maybe you want a venom that helps to degrade the muscle of the mammal so that is they're easier to eat because basically you didn't eat on a single bite. So maybe the venom, it helps digestion, helps degrading the muscle. Besides of that, in this particular snake species, there were some indications that there could be a lot of variation because people have looked at the venom in Colombia and Brazil, and it's different, even in just this is only adult snakes, depending where the snake lives. So, you know, if the place that they live makes such a bit of a difference, maybe their age also makes a big difference. So that was my first research project about. And this is what I tried to do, something called venomics. I'm not gonna go into detail in any of this, but whole idea is that you take the venom, you dry it, and then you try to separate the components of the venom. Venoms are mostly proteins, so you try to separate the proteins using typically something called liquid chromatography, just separates the proteins out, or something called electrophoresis, which also helps you separate proteins using a different mechanism. And then apply also mass spectrometry tools. Mass spectrometry was in the title of my presentation, and I'll come back to mass spectrometry because it has followed me through the years. But using different analytical methods, either to separate or to characterize the components on the venom of the snakes. So this was the plan. This was the idea. And throughout my thesis semester, I probably spent first month or I don't know how long just reading, trying to find the best conditions, the best protocols. This is what I had to do. This is what I need to do. And when I actually tried it, I got something like this. And this might not seem bad to you, but these are the results of a liquid chromatography separation. So you're expecting to separate your proteins over time. So you expect a lot of little peaks, each peak being one of those proteins. Something like this. This is kind of a textbook liquid chromatography result. You see all these little peaks. Each of the peaks corresponds to a component that you're separating over time. I was getting an abomination, a blob of nonsense. So it was very sad. I spent so much time just trying to find the best way to do it. And when I did it, it just didn't work out. So there is a lot of failure and in any scientific career, and certainly mine. But dealing with failure is probably the most important thing that you learn to do. There's going to be way less successes than failures. And so you cannot let single failure let you down. And you just have to try again. So for months, I tried and I tried, and eventually got to something like this. It's much nicer. On the top, you see the venom of the adult snakes. On the bottom, you see the venom of the baby snakes. And so you see some differences. Example here, baby snakes has more of these peaks, and adult snakes has more of these ones than baby snakes. And so what are those peaks? How do we know what they are? Well, that's where mass spectrometry comes into. So mass spectrometry gives you results like this. They're called mass spectra. And with them, you can basically find the mass. How heavy is the molecule that you're analyzing? So I could get the mass of these proteins. With the mass, because snake venoms have been characterized many times, and there are just particular classes of proteins, you can actually classify them. So these are the neurotoxins, which I mentioned before. They will probably be more abundant on the baby snakes, and they are. And these are the tissue degrading enzymes. They are more abundant in the adult snake, as we expected. So everything made a lot of sense. But let me expand a little bit on what the hell is mass spectrometry, because from now on, everything is going to be mass spectrometry. Well, not everything, but a lot. It's a very short video. Well, it's a long video, but I cut it. I found from the Royal Society. It's pretty old, so it needs updating, but it tells a bit of what is mass spectrometry. And I hope you can hear the audio.
So we don't hear any audio.
You don't hear any audio? Okay.
No, not yet.
So I'm just going to repeat what this lady in the video is saying.
Okay.
Basically, mass spectrometry is a molecular balance. It will just allow you to measure the mass of molecules. And so there are many different types of mass spectrometers. One of the ones that she's showing, and actually let me jump to this. Yes. Okay. One of the ones she's showing looks like this. Basically, you generate ions from your sample, and what are ions are just charged molecules. And then you shoot them across your instrument. And so because they are charged, think of magnets. So if you have a positive charge, it will be attracted to negative side of the magnet, for example, and it will be repelled by the positive side of the magnet. So mass spectrometer at the end is just playing with big magnets. So you can use the magnets to deflect charges of the same sign or attract charges of the opposite sign. And depending how strong is your magnet, you can deflect more or less the big or the small charged molecules. And that's how you separate them out. And this is what it's showing. So for example, you want all your molecules to follow this path. But if you have a molecule that is too heavy, it won't be able to be deflected correctly by your magnets all the way through to your detector that is over here. So it will collide somewhere here. If your molecule is too light, too small, it will be deflected too much. And so it will collide somewhere over here instead of going all the way through. So you're selective to the mass of your molecule, and that's how you separate. Nowadays, there are many, many ways to do it, but the basic principle is just that, is using magnets or electric and magnetic fields to move ions across and do with them whatever you want them to do in order to separate them by mass. So that's what I started using, and that's what allowed me to classify these different proteins into different classes. So that was cool and all. Then we tried to do other techniques. I'm not gonna go into detail, but for those other techniques, we needed some reagents and some enzymes that we didn't have in the lab. So we ordered them, from the US, which makes a lot of these reagents. They got to Colombia when I was already in grad school. They took about 2 years to arrive there. And that tells you a bit of how much more difficult it is doing science somewhere outside of the quote unquote first world. So this never really ended, but it's a project very dear close to my heart. It was the first time that I had a chance to deal with research on my own. And so that's what started everything. And when I was finishing the actually this had been finished, I was just finishing my second major in industrial engineering. I got the chance to come to Purdue and get a fellowship to be part of this summer undergraduate research fellowships program. And this is where Andres shows up again, because it just happened to be a coincidence that he was a grad student at Purdue at the time, and he ended up being my mentor. It was absolutely random. Nothing was planned. He just happened to be assigned as my mentor while I was working in the lab of Professor Jonathan Wilker at the chemistry department. And so, people come back again to my story. And so Jonathan had a crazy idea, and because he leads a group mostly working on adhesives and different ways of making best and better glue. And I was this kid that wanted to do analytical chemistry. So again, measurement science. I'm like, okay, I'm going to give you a project that you can measure things. What I want you to find out is how strongly do oysters stick. That sounds kind of ridiculous, but they try to mimic a lot of the adhesives that you find in nature, and oysters produce a very, very strong adhesive. So finding out how strong it actually is a very interesting question. And he wanted me to find the adhesion strength on baby oysters and adult oysters. Again, this was not planned. It was just randomly that this whole problem of baby and adults comes back to my life. But these are how baby oysters look like. I don't know if you've ever seen one, but they can grow in tanks in the lab, and they will just basically stick to whatever surface you put in. So you can grow them in like microscope light of different materials and so on. They will look something like this after a couple of months of growing. And then the question was, how am I going to measure how strong these things stick to the surface? It was completely out of everything I've done. I mean, I show you venoms and proteins and separating out and finding their masses. Now, what does anything of that has to do with it? Well, nothing. So I had to learn how to do a new measurement. And it took a while trying to follow this crazy journal idea and then Andres help. We ended up with probably the most out of the box solution. We're using one of those water flush things. So we're just using it to spray a water jet to a surface. Why? Because when you spray a water jet to a surface, you generate a force that you might not think of. You're not only generating force in the same direction of the flow, but also horizontally. That's called a shear force. That horizontal force can detach things around. And actually, you can convert that force into the adhesion strength of whatever you're detaching using the area of that thing you're detaching. So we took that water floater and improvised a little setup in which we can put a microscope slide under the floater, which is going to be held like this, just like laps forward on a shaker so that the slide can move around all like this. And then I spent weeks calibrating the floater so that each setting of the floater will have the appropriate force correlated to the flow that was coming out per time. So it was fun. And this was all built from the ground, from the crazy idea.
Nick?
Okay, so using the super improvised water floater device, we're able to actually calculate the strength of the adhesion of the spot, which is the baby oysters. But now the question is, okay, then what do we do with the adult ones? The adult ones look something like this. Just a bundle of oysters to stick to one another. Of course, the floater is not going to work here, so what are we going to do? Well, I took all these bundles and with one of those spinning saws that you used to make like wood work and so on, I chopped and chopped and chopped hundreds of oysters, which I feel too many oysters in my lifetime by now, and selected the best pieces that had flat sides, both sides. You can see here the adhesive between both oysters. And so that is the adhesive that we want to measure how strong it is. Then with the strongest adhesive I could find, this epoxy resin, I stick nails to both ends of the Oyster. And then we put on a commercial instrument that is used to measure adhesion strength. So it will just pull apart something like this. And then depending on what force you use to pull apart, then you can calculate the adhesion strength. And so we did this with many, many pieces of adult oysters to find a range, which is way, 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 way higher than the one of baby oysters, as expected. So very out of everything I've ever done in my life, but I learned a lot of things in maybe to think outside the box to solve measurement problems. But again, with the coincidences, it was when I was in surf here during that summer that I had a homework as part of the program because we were taking some classes. That was to meet some faculty that are not the faculty you're working with. So I sent a lot of emails trying to meet a lot of faculty in the department, and unsurprisingly, almost nobody replied. Now, one of the people that replied was this person here, Professor Graham Cooks. And we set a date and time, and just went there that we were going to talk for 10 minutes, 15 minutes, whatever it was. And no, he took probably a whole morning, hours and hours. He took me to every single part of the lab, told me the story of every item around. Whenever he had to leave for a meeting, he let me one of his grad students to 3D print something for me. He didn't have to. Just a random homework from a random kid from a random country. Why would he care? And he did. And so at that point, everything I could think was, if I ever had a boss, I would like to be someone like him. And eventually, when I decided to apply for grad school, I did apply to Purdue, and this man ended up being my boss and my mentor for the past 5 years. And it all started with that random homework. So another of the big coincidences part of my life. But yeah, so that's why I am where I am now. In any case, Graham at the time was working in some forensic applications. Particularly, one of his grad students, Patrick Fettig, was working on that. So he put me in contact with Patrick. And from day one, when I arrived to Purdue, Patrick picked me up, turned me around, let me be part of all the experiments he was doing. And I was with him literally almost 24/7 when I was not taking classes. He gave me a chance. He didn't have to. And he did. So very grateful of that. And then he convinced Val, which was a postdoc, the third person in this slide, to let me also work with her. She was an expert in toxicology. She was doing a lot of drug monitoring and drug detection for forensic applications. So convinced her to let me work with her, and I started doing that. And the first thing that we did together, the three of us, was using swabs. So the same ones that you will use at the doctor's office for like a strep throat testing. But now to find out if someone did drugs. So just take the swab, a little bit around your mouth, and doing absolutely nothing. Apply some voltage to the swab, and that will generate ions. So again, this is a different ionization method. Form those ions that you need to go inside the mass spectrometer that will separate them and so on, as I mentioned before. So we're able to quantify more than 30 drugs of abuse, all sorts of cocaine and opioids and antidepressants and antipsychotics using this method that it's incredibly fast and can be done, for example, at an office right there without having to send samples to the lab, because you just take the same swab and just spray it in front of your instrument. So that's the first thing that I work at Purdue. And of course, I was in Cloud9 because I was working on forensics with this too. And so it was a very nice time. And with Patrick, we did a little bit more forensics instead of swabs, and we were using paper. And what's very cool about it was that we were using these very small instruments. So don't mind what is a Raman, but it's an instrument that also is used for chemical analysis. But it was the size basically of a smartphone, maybe like a walkie-talkie. Very, very small. And we were using a mass spectrometer that, compared to the one I tried to show in that video, is very, very small. This thing is between the size of a toaster and a microwave oven. It's a very small instrument that you can just put it on the back of a police car. You could go to a crime scene and do your analysis with both instruments at the same time, just from a paper, simple, plain old paper. And so this allows you to identify and confirm, for example, drugs or explosives at a crime scene. And that setup made it portable, so you can take it to the crime scene. You don't have to send any evidence back to the lab and go through the whole chain of custody and so on. But you can also make that evidence valid in the court of law, because the court of law requires that you have at least two independent analytical methodologies to say that something is on a sample. And so they give you two different independent and orthogonal analytical methodologies to do that on the field. And yeah, so again, I was working in forensics. I was living the dream. Then Patrick graduated, Valentina found a job, and so everyone kind of fell apart. And I was left alone, and funding reasons and so on, I had to jump to a different project. And so I ended up working with this thing called desorption electrospray ionization. I landed on this project, and this is what I've been doing for the past 3-4 years. So what in Earth as desorption electrospray ionization is another ionization method. It's another way of producing ions. In this case, you're using a water jet, very similar to like the floss, the water flossing, but in a micro scale. That impacts on a surface, as you will see in this animation in a minute. And then that generates a small splash. And then that small splash in these little tiny droplets carries the components of your sample, which your sample is deposited here, to the mass spectrometer as ions that you now are going to analyze. And so I was very excited, and because there is no sound, this is not going to work. I'm just going to show you something. This is my advisor when he was giving a lecture for an award. But this technology was featured in CSI. Imagine how happy was I when I found this out. So if you ever had a chance, go watch this clip of CSI explaining what DESI, which is the acronym for desorption electrospray ionization, is. They basically, in the CSI episode, they use DESI to analyze fingerprints and find the components of whatever the suspect touched. This is a very cool thing. And that was one of the main applications of DESI. For example, fingerprints. If someone touched, let's say, cocaine, you can see the cocaine besides just the fingerprint pattern that you will get with your typical methods, because you get chemical information out of it using these little droplets to carry your compounds to the mass spectrometer. You can also image tissue. And then if you image tissue, you can image tissue that is cancerous or non-cancerous, and you can tell it apart. So it has applications in clinical settings. But what I've been using it for is to analyze many samples very rapidly. If you think of a fingerprint or a tissue, in essence, they're just a bunch of chemicals with some sort of a special distribution. And you, of course, care about the special distribution. So nothing is stopping you to create your own arrays of mixtures of chemicals with a special distribution that you define. So you can create arrays of little spots, and each spot can be a different sample. Each spot can be a reaction. Each spot can be a biological assay. Each spot can be a biological sample of sorts. And so you can analyze them all really fast. You can just raster across. So these arrows are just indicating you how that spray, that jet that I was talking about, moves. You can raster across and basically create an image. Or what we're doing right now is use a little bit more of technology, some custom software development, to be able to jump. So each one of these circles that you see here are just samples. And now we can control our system to jump from sample to sample. So we're spending less than a second in each sample before jumping to the next one. So we're analyzing things really fast. Closest methods take a couple seconds, 10 seconds, a minute or so to analyze samples. We're being in the sub-second realm. So for example, this heat map over here has 6,000 samples. We analyze that in about an hour, getting all the chemical information out of it And again, chemical information means that you can find what is in those samples and how much is of those things in those samples. So this is how the current platform works. We have a lot of custom and commercial robotics. So this is a robot that allows you to pipette samples, prepare samples, move samples from places to places. Here our samples were displayed, and then we transfer very, very small amount to this white plate that you see here. Then the plate is automatically transferred to the back, where we have a shuttle that gets triggered. And there's another arm that will take the slide and put it on the DESI stage. So this is where the ionization happens, and that is the mass spectrometer. Skip this part. We have custom software to do the calibration. This is how the data looks like. So if you remember a bit of the results that I showed before, it's a mass spectrum. And so it shows you the masses of different things that are on your sample. And this is how it looks in real life, the DESI stage when it's moving. The solvent spray is coming this way, and the little droplets are being sucked inside the instrument through this capillary. So you see that the stage is moving, kind of jumping sample to sample, spending less than a second on each sample before jumping to the next one. We've done all sorts of things with this platform. So if you've taken organic chemistry and you like organic chemistry, we've done synthesis, so creating new molecules. For example, if you want an anti-cancer drug like this one, lomustine, because we can analyze 6,000 samples in an hour, we have so much room for so many experiments that we can try different combinations of solvents and, for example, different amounts of different reagents, different temperatures for the reaction, what reagent you add first and the other one, and so on and so forth. You can test all these possible combinations of conditions to find the optimal conditions to synthesize this thing. And of course, then that you can translate that to a very big scale in which you actually produce grams and grams of this thing per hour. We can also modify the compounds to generate analogs, screen all sorts of combinations of compounds, and so on. We can also do stuff on the biological space. So, for example, study enzymes, how enzymes do the reaction, how fast they go, do they get inhibited by things, do they not, can they be reactivated? We can also sense receptors, how the receptors bound to molecules or not, and everything, all of this is done by analyzing thousands of samples, spending less of a second on each sample. We even have done clinical applications, so we can put tissue biopsies, these are brain tissue biopsies, transfer them to one of those white plates that I show you in the video, and then we can tell apart them by which ones have high concentration of tumor cells compared to low concentration of tumor cells. We can put bacteria under it and then profile the bacteria, or being able to tell which one of these bacteria colonies produce something that the others ones don't. And right now, what we're pushing it is to do drug discovery, because we can do the organic reaction, so we can synthesize many compounds. We can also do the biological assays, so we can test the activities of those compounds against an enzyme, bacteria, a virus, for example. Let's think of COVID, test their biological activities, and then be able to select those that have good activities, modify them, so change a little bit of their structures, and test them again to see which one of those tweaks that you made increase their activity. Go over this cycle over and over and over again until you find the best molecule you can get that will eventually go down to further studies and clinical trials and so on, and hopefully, maybe eventually will become a new medicine. And so we're doing all these operations with the same technology, which is DESI mass spectrometry, within the same single platform, all in one. And that's really where we're going. And so this is the last thing that I want to tell you today. It's an example that goes more or less all across this drug discovery cycle. And that started with Professor Andrew Massacre and Samadhi, one of his students, just reach out and ask us to help them with an enzyme problem using our platform. And it turned out that this story actually started more than 10 years ago in our lab. We're using DESI, if you remember, I told you they can do image tissue sections. It was found out that if you look at prostate cancer compared to normal prostate sections, you find a lot of this random thing called cholesterol sulfate. a lot in the tumor, nothing in the normal. So why? Well, that led to a decade of research at Purdue and other places that found out that you don't only accumulate this cholesterol sulfate, but you actually accumulate the enzyme that produces that cholesterol sulfate. And so that indicates that this enzyme might have some correlation with the prostate cancer. And actually, if you force the cells to kill that enzyme, if you delete that enzyme from the prostate cancer cells, they die. So this indicates that it's a very interesting and currently undrugged target for prostate cancer treatment. And so that's where we're going. So now we're using this technology, again, putting all those 6,000 samples on those plates, going super fast to characterize the enzyme so we can study how fast the enzyme converts cholesterol to cholesterol sulfate. We can also analyze other different steroids. So there are cholesterol-like molecules that are also substrates of the enzyme inside your body to see what kind of affinity, speed at which those reactions are carried out. We can also use the system to screen inhibitors. So we can create or buy compound libraries with thousands and thousands of possible drug candidates and test them. And we get very high performance to test them. So whenever we find a hit, which is something that seems that has some inhibition for this enzyme that we want to kill, because it seems that killing it might kill the cancer cells, we can also do dose response curves. Basically, that means just changing the concentration of those inhibitors to see as you increase the concentration, if the response that you're obtaining, so killing this enzyme, inhibiting this enzyme, actually increases. And we do see that with some inhibitors. And then we can even go to cells. So we can take the prostate cancer cells and measure directly from those prostate cancer cells if you're inhibiting the enzyme or not. This is how the raw data looks like. I've showed you nice little plots like this one, but all that information comes from the mass spectra. That is what shows you what molecules of what masses do you have and how much of them you have in your sample. And so in this way, we can tell if an inhibitor is working directly from the cells, from the prostate cancer cells, and also we can see if the cells are dying or not. And in this way, then, this all started from a random observation that cholesterol sulfate accumulates in prostate cancer tissue. And now, through the years, has driving us to being able to actually try to find new drugs to inhibit this enzyme to try to treat advanced prostate cancer. And so that is what we're pushing right now, not only with prostate cancer, but in other areas. And we really hope that this technology can make a difference in the way that people do drug discovery today. And with that, I think I won't take much more of your time. This is the last year's picture of my group. This is all the people. Some of these are working on this project. Some others are working on other very interesting stuff. And of course, all the funding agencies that make our work possible. But thank you, and I'll be happy to get any questions through email if anybody's interested or anything or wants to know anything about research. Wants a tour of the facilities, we will be happy to give tours to you guys. Anything, we will be very happy to hear from you.
Awesome. Awesome. Thanks so much, Nick. That was such a comprehensive view and such a wonderful story, all the way from snake venom and looking at how oysters stick with John Wilker and Andres again. What a coincidence, huh? To come find Andres here again. And I had interacted with Andres when I was at the Binley Bioscience Center. So it's so funny. Because he was interested in the snake venom and understanding the proteomics and so on. So neat, so neat. And this whole thing on mass spectrometry, it is such a wonderful piece of work that I hope people understand as to like the application is so broad. There's so many ways that we can use this type of work, this type of research. And as you've shown one way is this cancer, prostate cancer screening and prostate cancer drug discovery approach. So neat, so neat. I'm sure that people that are going to watch this program are going to say, wow, what is next? What else comes next? And I don't know if you can tell us a little bit about perhaps what are you thinking will come next in your career, and then also like what comes next in this type of technology? Where would you take it if you had it to take along with you?
Yeah, so that will come next for me. That's a very good question. Currently unresolved. On my last year here, I'm graduating this summer, and so I'm still trying to figure out what's gonna happen with me. Um, I'll let you know whenever I know, because
Okay.
currently I really know nothing. But about this technology, we do know. So right now, really, we're building the version 2.0 of the system. So with support from the NIH and the National Center for Advancement of Translational Science, NCATS, we're building this new platform, which is going to look and work much better than the current one that we have, as a single unit that basically integrates two commercial components so that it can actually be commercialized. Because currently this technique is unique, it's exclusive, and it only exists here at Purdue as a facility for everyone to use, but it only exists here at Purdue. So what we want is to put it in the hands of the people that can use it. And you can make more impact if more people actually use it. So we're trying to commercialize it. And the way that we're trying to accomplish that is going through these two companies that integrates the robotics and the mass spectrometry side of the system, put it together into a single integrated, fully automated unit. And so that's the one that we're building right now. We have a bunch of boxes in the lab for that reason. So hopefully over the next couple of months that will start taking shape. And in a year's time, that platform is going to be sent to the NCATS Aspire lab in Rockville, close to DC, to their headquarters. And so they're going to start using the platform. So we already put one system there. One alumnus from our lab already acquired the same platform, basically using the same design that we made, the 2.0 design that we just created for his lab at the Navy Research Center in China Lake in California. And we're trying to convince more people to start getting them now that it's more like a commercial product. So hopefully we accomplish that goal.
Well, what's so exciting, it's so exciting because, like here you are, you're finishing a PhD, you're doing all this hot research, hot innovation, just at the edge of the technology, and you get to also see that part of the commercialization and all of that. What a wonderful opportunity. Nick, thank you so much for talking to us today and giving us a glimpse of some of the exciting work that you're doing and the journey that brought you here and the journey that brought you to scientific research is so exciting. Thank you, Nicolas Morato from the Graham Cook's lab in the Department of Chemistry at Purdue University. Thank you so much, Nick.
Thank you for the invitation.
Absolutely. Have a great afternoon.
You too.
Thank you.